Good evening, everyone. Thank you for those who made it here to Bottacin, and for those of you who are online. It's a very rainy day, a little bit of a climate changey day, I would say. We are in May and it's raining, it's pouring. And my name is Francesca Sirocco, and I'm the director of NICHE, the new Institute Center for Environmental Humanities here at Foscari, University of Venice. And I'm delighted for Carlo Barbante's accepting, for his saying yes to our invitation to be here together with us. This lecture is in collaboration with the other center, with our sister center, directed by Professor Achille Giacometti, and the European Center for Living Technology, also based here at Bottacin in Venice. And we have, from the beginning, really tried to collaborate since NICHE was created a few years back. And this is one of the numerous events on which we have really tried to share knowledge and create a community of engaged scientists, practitioners, and humanists working together on these issues. So without further ado, Carlo Barbante is going to tell you a few words about himself. Of course, he needs no introduction, but the theme, of course, today is the climate crisis and human responsibility in navigating the Anthropocene. Thank you.
Well, thank you. Thank you very much. It's a real pleasure to be here this afternoon in a rainy Venice. I mean, and the point that I want to tell you today is that, well, I want to tell you a story. I want to bring you hand by hand and telling you what is happening to our planet. Well, as said, I'm professor at Foscari. Well, since a few days, because I was back from my directorship at the Institute of Polar Sciences, and now since May 1st, I'm back in the faculty team of Foscari. So where I spent, I would say, most of my academic life. Briefly, as I said, the situation from a point of view of global warming is changing quickly, and as we said often, the Venice is drowning. I mean, because the episodes of high tide in Venice are more and more frequent. And we try to understand and to see whether we had analogous in the past, and I want to briefly tell you a little bit about that. So most of the things that I'm going to tell you is, or at least part of the things that I'm telling you is taken by the last AR6, the assessment report of the IPCC, and especially dealing with the physical science basis. So what we know about climate. We know quite well. If we go back in time, we can retrieve information about our climate going back in time millions of years. And especially, this is the climate of our planet reconstructed from different archives. And when I say archive, I mean geological archives or sedimentary records, ice cores, tree rings, lake sediments, and so on and so forth. So we can go back, especially with geological archive, down to more than 60 million years ago. So where we were living in what is called a hot house planet. So no ice on Earth, temperature higher than 15 degrees than it is today, or better, the reference value here is fixed in between the average temperature in between 1961 and 1990. So as a reference, whatever is higher than that is a positive anomaly. So it's a delta plus, and what is lower than that is a negative anomaly, is a minus. Well, you see, I mean, the climate over the last 60 million years was dropping down and cooling. That is a well-known effect. Is an effect that has a lot to deal with the greenhouse gas effect, with the carbon cycle, and with the weathering effect. So the component of the happening at the geological time scale, the fact that when we have higher CO2 concentration in the atmosphere, we have higher acidity, and this is scavenged because of the acid rain that wash the rock and withdraw CO2 from the atmosphere. So it's a very long thermostatic effect that we live with that since 4.5 billion years, more or less, or since when we have an atmosphere. But the most important thing that is interesting us is the last few million years. So I would say something like in this period of time, you might see that there is an expansion of the scale over the last 5 million years, and then another expansion during the last few hundreds of thousands of years. And you basically see cycles over here. So you see cycles which are tightly linked to orbital parameter of climate change. So the position, the relative position of the Earth compared to the sun. So the amount of energy that is arriving today on our planet on this Bottacin is not exactly the same amount of energy arriving at the same time, same day, 100,000 years ago. So that makes a huge difference in terms of climatic cycle. And this is the reason why we have this ice age and interglacial period of time. And we are living today in a very special period of time, which is an interglacial. So we have in between two glacial cycles. And the most important thing is that the current interglacial, which is called the Holocene, is one of the most stable in the last few million years. So we never had 10,000 years as calm as we have today. We will come to that in a minute. So we are currently here, more or less at the end of this, or better, we are here where you see after what we call the Holocene optimum 10,000 years ago, the temperature were more or less stable, plus minus 0.5 degree, and then it started rising again after the Industrial Revolution. Well, we will discuss it a little bit better, but what I want to point out is not just the reconstruction of the temperature, we can do quite well, but also to put together CO2 record that we know from ice cores. We will come back to that in a few minutes, but we also know, looking at other proxies, other substitute of CO2 concentration in the marine sedimentary records and in the rocks, especially looking at beryllium isotopes in the rocks. And you can see how close the cycle of the temperature is with the cycle of the CO2. So higher CO2 means higher temperature. But what is really worrying, and if you want to put in the right perspective what is happening today, we should carefully look to what happened in the past. And there is a lot of our future in our past. So if we compare this graph that cover the last 65 million years with the projection of the IPCC compared to the future emission scenario, you'll see that the next 300 years, which is nothing on a geological time scale, are pointing out to different scenarios. So it means that in 300 years, in the worst scenarios, we can reach temperature that we had 65 million years ago, with a higher value of about 12 degrees, with a sea level rise of hundreds of meters higher than today. So, well, of course, it will depends where we will be able to stay within these different scenarios, and that would be dramatically important to set up mitigation policies in the future. So the reason why we are bringing together a future projection and the past is, as I said, because there is a lot of our past in our future. And one of the most important things we are looking at is that whether the planet is warming. I often show this graph that is called the climate spiral, that brings together temperature across the year from across the month from 1880 to 2022. You see that temperature around the clock is turning around, but as you see, is moving toward the external part of the graph, and you have more or less the average value, what we say the reference value. as I say, the average temperature from 61 to 90, compare to the temperature that we are recording today's and in the most recent years. You see the clock moving into the central part of the graph, and if you put in the right perspective, you turn the spiral upside down, you'll see that that something changed in the most recent years. So we have already we went already above the 1.2 degree warming, which is a lot, is what we call from a paleoclimatological point of view, an abrupt climate change, so something that is happening in a very short period of time. And this average temperature is not equally distributed. Again, if we look at this animation, again, from the temperature anomaly during the period of time 1880-2022, you'll see that we had a period of time in which we had cooling in part of the world. The period of time 1880-2022 is where we have instrumental information, and we have a global grid of temperature, that reconstruction of the temperature, that are very, very reliable. So basically, you'll see that in average, we had about 1.2 degree from increasing the temperature from 1880 to 2022. But the temperature is not equally distributed. We have part of the world that cooled. For instance, some part of Antarctica here, some part of the Pacific Ocean, northern Atlantic, but we had other region of the world that warm up dramatically. Just to give you an idea, the Arctic, which is very sensitive to global warming, is rising its temperature, especially during the last few decades, at a pace which is about 2 to 3 times higher than the average velocity, and the same in the Mediterranean basin. Just to point out this anomaly here, this is what we call the hotspot on climate. If you look at that, well, this is again a graph that bring together the global temperature change over the last few century, a little bit more than that. You see that is a scale which is a little bit compressed, but because I want to keep the same scale looking at the Mediterranean basin. So if you look at that, this is the temperature change in Italy, which is much bigger than what we have seen from a global point of view. Is more than double. This is the reason why we say that the Mediterranean basin is an hotspot, and in fact is reflected with the dramatic impact, for instance, on the temperature, on extreme events, on melting of the glaciers that we will see in a few minutes from now. And we know that the interlink in between the cause and the effect, we call it attribution, and we can attribute very well the current warming to anthropogenic activity, and especially to the emission of greenhouse gases. We know it because CO2 and methane are polyatomic gases. We know the length of the chemical bond. We know that the interaction in between the emission of radiation from the planet, from our planet, and those little tiny molecules can excite the molecule itself, and then vibrating that make the atmosphere warming. And we know that a very little increase in this concentration of greenhouse gases, which are what we call trace gases, can influence a lot the temperature of our atmosphere. And we do also have modeling exercise that help us a lot to attribute the current warming to the greenhouse gas emission. If you look at this report, is a graph that is reported in the IPCC report, in the last one, we see that over the last 2,000 years, we have again the last part of the Holocene with some little changes. The gray area that you see here is due to the uncertainty that we have to reconstruct the temperature because of most of this reconstruction comes from tree ring. So this is the uncertainty. But as a general trend, we have a slight cooling, which reached the minimum of the temperature around the so-called Little Ice Age at the end of the 19th century. And then we had the Industrial Revolution, the emission, and the huge increase in the year 2000s. Well, if we zoom into the last 170 years, so we go from 1850 to 2020, We see that in black, we report the same curve here, so that the observation that we have overall globally all across the world. Well, we do have models, climatic models that are, I would simplify as a mathematical equation that describe the way in which the parameters, in this case the temperature, react to some changes. And we can reconstruct, given specific input, given the input of natural radiation, volcanic forcing, the relative position of the Earth compared to the sun, and the anthropogenic input of greenhouse gases that we know very well, we can calculate what should be the temperature. And indeed, we can use this model and reconstruct in, you can very well see the brown curve here that mirror perfectly the observed concentration. So the model we are using are quite good to reconstruct the observed change. But then is a model, so we can play with the model in the way we want. And if we simulate the temperature of the last 2,000 years, or if we concentrate in the last 170 years, without, or better, neglecting the input of anthropogenic sources, so neglecting the fact that we emitted a lot of CO2 and methane and other greenhouse gases during the last few centuries. Well, if we simulate just taking into account the natural emission, we see that the results of the model give us a pretty constant temperature for the years from the 1850 to 2020. So the missing part here is definitely coming from the anthropogenic impact. We do have another well-established confirmation of the attribution of climate change. Well, we do have facts that we know, I mean, which are undisputable facts. And if we look at that, if we look at the concentration of greenhouse gases in the atmosphere, well, it is the highest, at least in the last 2 million years. We know that we have to go far back in time, at least 6 million years, to find similar CO2 concentration. And we get most of this information out of the ice core analysis in this part of my research field. The ice entrapped the little tiny bubble into its matrix. So when you extract the ice cores, and I'll show you in a minute, you get little tiny bubble into the matrix, and so we can get information out of this. This air is a sort of fossil air entrapped into the ice. And ice cores, compared to other archives like marine sediment or rocks, hold an important feature. Is the only archive that at the same time gives you information about the forcing, so the greenhouse, the dust, and so on, and the response factors, the temperature, precipitation, and so on. So you have on the same archive cause and effect of climate change. Well, what we do, we go in very specific places like in Antarctica. We are actually drilling where the red dot is at the moment, to retrieve a very deep ice core, because snow falls and accumulate year after year and trap the chemical substances in the surface, and trap the bubbles of air, which at least at the surface, the air diffuse bottom from the top to the bottom. And so we can dig into this ice down to thousands of meters and retrieve information of the past atmosphere. So we can analyze CO2 thanks to a very sophisticated method, and in this case we can reconstruct the changes in the temperature during the last 800,000 years. And what you can see, I mean, is something like this. I mean, CO2 oscillate with following, and we will see that in a minute, following the rhythm of the temperature over the last 800,000 years. But the most important things to note is what happened in the last few centuries, where CO2 concentration went up to something which is absolutely out of scale. It can be seen even better here in this graph, where we can see together what is recorded in the ice the CO2 concentration, the temperature, so you can well recognize the cold and warm period. You can recognize it in blue and red. The last few climatic cycle, where you see this huge oscillation with a periodicity of about 100,000 of years. We can discuss a lot about the periodicity, but it's not now the time to do that. But what I want to tell you is this huge increase in greenhouse gases. So it goes outside the screen. Well, if you look at that, CO2 concentration always oscillating between about 180 part per million and 280 part per million. We are well above 420 today. So something that we know directly from the study of the fossil atmosphere that we never had in the last 800,000 years. And even if we go and look at the marine sediments, where we can indirectly extract information, we know that for the last 6 million years, we never had something like that. And the point is that CO2 is a greenhouse gas, and it stays in the atmosphere for quite a lot of time. So if we would quit today the emission of CO2, CO2 will stay for a long, very long time in the atmosphere. And nobody inside this room, nobody living in the planet today will see the CO2 concentration dropping down again below the 400 part per million. So it will take a lot to restore the concentration. Well, let's see other facts. Of course, associated with the increase of the temperature, one of the most important impact is the increase of the sea level, and we have the fastest rate over the last 3,000 years. We never had a sea level, an average sea level increasing so fast. This is an example, since we have a satellite radar altimetry, which is very, very precise, and we know that since 1993, and we had longer record because we have mareographer measuring the sea level rise. We know that we never had a very high speeding in increasing in the sea level. In the period of time in between 1880 and 2000, the increase of sea level was of about less than 2 millimeter per year. Since we have the satellite measurements, so at the beginning of the 90s, we know that from that decades, 93, 2002, we had about 2.3 millimeter per year. In 2.3, 2012, we have 3.3 millimeter per year. And what is happening today is that we have more than 4.5 millimeter per year increase. So the speed, the pace in which the sea level is increasing is dramatically high. So over the last century, we had more or less always about less than 2 millimeter. Now we are going at a pace which is higher than 2 millimeter, 4 millimeter per year. So that's really dramatic. And if you say that 4 millimeter is something like that, if you multiply by 10 is something like this. Even if you multiply, and also thinking that it's not a linear increase, is an exponential increase, well, I let you imagine what might happen into the future. Well, another thing that is extremely important is the Antarctic and the Arctic sea ice. Sea ice is dramatically impacted by the current warming. I'll also want to show you a graph, which is this one, and show the annual Arctic sea ice minimum. Since we do have, again, satellite measurements pretty well accurate since 1975, where we had about 6.8 million of square kilometers of sea ice in the Arctic. And it was thick sea ice. We had area in the Arctic where we had more than 4 meters thick sea ice, especially in the central Arctic, in the central Arctic Ocean. So very thick sea ice. And everybody, when think about the Arctic, we think about exploration and huge pack of sea ice, very thick, trapping the vessel. This is an example of the Erebus and Terror in the Arctic during the exploration. Those two ships were lost because of the sea ice, but and that was not that far from the North Pole. And I tell you, and in our imagination, the Arctic is like that: a huge, thick, vast, immense field of sea ice, and very, very thick. Well, I was in the Arctic at the North Pole last summer with an icebreaker, and I want to show you the last few miles reaching the North Pole. So this is a time lapse taken from the icebreaker. Well, there was ice, sea ice. The thickness was about half a meter. Nothing thicker than that. A huge part of the sea ice at close to the North Pole was not sea ice, actually. It was open sea. So we have to completely change our perspective of what means to have sea ice in the Arctic, because that's no longer as we had a few decades ago. And you see, that's when we reached the North Pole. That's exactly the North Pole. So it was almost open sea at the North Pole, and that was the end of August last year. So our perspective has to change completely when we think about the sea ice. And there is of course, a clear link. We know that the sea ice is disappearing because of the temperature, and we know that the CO2 and the temperature goes together. And there was a study a few years ago that point out the fact that of course you have a cumulative emission of CO2. And if you put cumulative emission of CO2, so how much CO2 built up into the atmosphere with the sea ice area in the Arctic, you see that the observation and modeling show you that the more CO2 you put into the environment, the more ice you lose, the sea ice you lose. And well, we can calculate that. It's more or less 3 square meters of sea ice area every cubic metric ton of CO2 that you emit. So every metric ton of CO2 is more or less 3 cubic meter of sea ice. Well, you can easily calculate how much your diesel car can contribute to that. So when you do, I just tell you that more or less, if you do a rough calculation with 10, when you refill 10 times the tank of your car, you contribute for a disappearance of more or less about, as far as I remember, about 10 square meter of sea ice in the Arctic. So when you refill your car, think about that. That is for the Arctic. Walk if you can, yes. This is for the Arctic, and until a few years ago, we thought that the Antarctica was in a steady state. So Antarctic sea ice was in a steady state, but recently, well, we see that there is probably a decreasing trend. We don't know. I mean, let's see what happens in the next few years. It's too early to say whether this is a real trend or it is a natural variation, but it's something we have to carefully consider about. Another fact that I want to point out is the retreat of the glaciers. Again, temperature has a strong impact on the glaciers, especially again in the Arctic, but also at lower latitude, like in the Alps, in the Tibetan Plateau. This is, for instance, the observation that we do have in Greenland. In Greenland, again, since the beginning of this century, we do have a gravimetric experiment, which is called GRACE, which measure, thanks to satellite, the gravimetry, and therefore we can convert into ice loss, all the data of ice loss. So again, the mass balance of Greenland. And we can calculate year by year, since more than 20 years now, how much ice has been lost from Greenland. And well, the ice loss in Greenland is pretty high. It's about 280 gigaton per year of ice. I can translate this number in real number. Well, it is more or less, and it contributes to more or less to 0.8 millimeter per year. And okay, translating it is more or less 420 rooms like this, or swimming pool, more or less, per minute. So every minute, Greenland lose about 420 swimming pool melted into the sea. Well, of course, this has a dramatic impact, because you inject a lot of fresh water into the North Atlantic, changing the density, changing the oceanic circulation, and so on. Well, and again, this is an impact in the Arctic. We do have impact also on other ice bodies. Everybody knows that the Marmolada Glacier is not that far from here. Again, is one of the most impacted cryosphere bodies in the Alps. I just want to give you a number. 2022 was one of the warmest year in the last decades. Well, the glaciers of the Alps lost about 6% of their mass in 1 year. 23 was also very warm. We lost about 4% of the ice, the mass of the ice of all the alpine glaciers. So in 2 years, we lost about 10% of the mass of glaciers, which are already under threat, because, you know, we had glaciers that were already very much stressed by the last few decades. So this is more or less the situation of Marmolada Glacier. For those of you who knows where we are, this is the Lago di Fedaia. This is the Marmolada seen from the north, and the fact that most of it is exposed to north preserve it a little bit. Well, we are now at this stage. We have 1850, so more than about nearly 200 years ago. So we were not at the maximum of Little Ice Age, but well, glacier were at pretty well expanded. So then we have no real data, suitable data, until 1988. So I just want you to see what happened already in 1988. We were at the beginning of the crisis and in the last few decades. So look at that, what happened in 2003, 2015, and 2022. So we are we have almost lost a glacier. We lost something like 80% of the total surface of the glacier, and more or less the same in terms of mass. So we are losing a lot of volume of water, of course, with all the implication. I mean, we are losing a resource, we are losing energy, because these glaciers bring into a lot of water in dams and hydropower, which is a big loss. Well, another example I want to show you, this is even more impacting because it's a visual example, is in Ghiacciaio di Felaria in the Eastern Alp. Again, 2022, another very, very warm year, as I told you. This is a time lapse. So look at the summer of 2022. In this time lapse, you can see the rock on the bottom left. You can see the ice tongue and how fast is decreasing his mass. So you see, you see the velocity in which the ice is losing his mass, and it can be even more evident if you put at the beginning and well, at the end of the summer. You see, we lose the length, we lose the area, and then we lose the volume. And if you look at the years, 4 years from 2019 to 2022 on the same glaciers, you look at in June 2019, the glacier was there. And then again, this putting together all this time lapse from a fixed camera, you see that the June 2020, sorry, that was May 2020, and then again the year after, it is June 21, and again 22. So it's a dramatic loss of water, you know, and a big huge amount of water loss. Well, look at the thickness as well, you know. So the thickness is really dramatic. This is tenth of meters of ice lost in a very short period of time. So, well, so there is a huge impact, and a lot of our future will depend on the so-called shared socio-economic pathway, since we know that CO2 and greenhouse gases is the culprit, is the cause of the global warming. Well, our future will depend on how good we will be to stay within certain emission. Well, whatever we will be able to stay within the very low carbon emission or the very high, that's really a challenge. Most likely we will stay somewhere in the middle, hopefully. But in any case, this will have a lot of impact into the future. And we can also look at for instance, at what will be the temperature depending on the different scenarios that you can see here in the right. We can look at, well, in the last few decades, again, 2024, the first few months are beating record after record. So we are most likely 2024 will be another record of temperature. I hope not, but as we started, this is really dramatic. And also we can have a perception of what other climatic parameter we'll look at. For instance, well, that's the temperature I've shown you already. The Arctic sea ice, again, another important parameters. So this is the future scenario easier in the right part of the graph. But what I also want to point out, regardless of the scenarios that we have in the future, the next 30 years are already committed. So even if we stop today to emit CO2 or another greenhouse gases, you see in the best scenarios, that is the social economical pathway that you see here in blue, for the next 30 years, we have basically no changes. And that's the reason why I told you that there is an inertia into the climate system. So whatever is in the atmosphere today will stay in the atmosphere for quite a lot of time. And again, for the sea level is exactly the same. Again, if we fix at 2020, the day in which we stop to emit CO2 in the atmosphere, again, for the next 30 years, we basically have no real changes, but the situation will change dramatically for the future. And again, those are different scenarios. As I told you at the beginning, the velocity of the sea ice, of the ice melting is increasing, and so is the sea level. And so we have different scenarios that in the worst case, we have more than 1 meters of increasing sea level at the end of the century. Well, someone says, and the most recent models, climatic model says that, okay, this data is already overcome by the new projection. So, let's see what happened. But the most important things that we have to take into account is this dashed line that we see here, and is what is called a low likelihood, high impact storyline. Because we don't know everything about the climate system. There are components of the climate system, especially I spoke about the Antarctica, you know, and especially if you speak about the Western Antarctica, where we have glaciers that are accelerating their melting because the sea ice is disappearing, and the effect of the stop effect that this ice sheet was doing on the ice shelf on top is decreasing its power. Well, if this happens, we have this low likelihood and high impact story that brings together into the future to something that is totally not completely foreseen. That means in the best scenarios at 2300, which is not for us, but it's not that far in time, we might have from 2 to 3 meter increase in the sea level, or up to 7 meters in the worst scenario. So there are things that are not completely under control. And of course, acidity is another important factors. We are increasing decreasing the acidity of the ocean, because CO2, which goes a large part of the CO2 emitted into the atmosphere, goes into the ocean, and the CO2 is an acid at the end. From a chemical point of view, is an acid, and it increases the acidity of the water, so decreasing the pH. So it's the so-called acidification, ocean acidification problem that together with the increase of the temperature of the ocean cause a lot of effect. For instance, an impact on corals, and so destroying hundreds of square kilometers of coral reefs. So that's a dramatic effect. So, well, again, I want to come back to this graph again, because there is a clear increased temperature with the accumulation of the CO2, and those are the different scenarios that we see, with a very high emission and the low or very low emission. And it depends how good we will be in keeping these low emissions, so to moderating the emission into the future. So, and I said in the title of my talk, we are navigating the Anthropocene, and it's not. I choose this title because you might remember, probably Achille remember, that a few years ago we give there was Paul Crutzen that came to Venice for laurea honoris causa. Some of you might remember, and it was in 2007. I collaborate with Paul Crutzen quite a lot in looking at the platinum group element in snow, to look at the cosmic dust flowing into the planet. So Paul came, look at myself, I am wearing Wellington boots. There was more than a meter of water outside, and Paul Crutzen, who is the man who invented the Anthropocene, is well known for having said that the Anthropocene. And when he saw me coming into the hotel with a Wellington boot, he told me, "Carlo, we are navigating the Anthropocene." So that's the reason why I want to put a little bit of Paul Crutzen into the title of my talk. And that's true. I mean, we are literally navigating into the Anthropocene, and we are literally at the turning point of our climatic trajectory. As I told you, we have seen that the Earth have been cooling and warming in the last few hundred of thousands of years, in the last few million years, because of the natural effect, the relative position of the Earth compared to the sun, the amount of energy arriving from the Earth. So from glacial, where we had very cold temperature and glacier flowing across the Alps also, and the Pianura Padana, and interglacial period of time. Well, if you look at the time coming toward us, I mean, we were on the left and on the right, but now we are really at what is called a planetary threshold, and it strongly depends whether we will move on a so-called stabilized Earth, so we will be able to keep the climatic boundary within certain borders, or we will fall into what is called the hothouse Earth. So we will fall into the future, where we have to live with some of the impacts that we are facing with high tides, more and more frequent. So we are thinking to something that, well, in the future, most likely, the barriers we have built to protect Venice will not be enough. So we conceived the MOSE in 1972 with a certain level of ranges of marea, of tides. Well, it took 50 years to have it in place. Well, we can't wait other 50 years. We have to start thinking what we do of this city for the next 30 years, because 50 years will be way too much. And well, and we also have to think to justice and to people that is living every day under the threat of the global warming, with increasing storm, increasing extreme weathers, and flooding. So, well, I think I'm over. I finished for my talk. I hope that I just wanted to bring you with me on a journey into the Anthropocene and what is happening to our planet. Thank you very much. Ready to answer a question, if any.
Yeah. I want to put in the highlight something that Carlo glossed over, because this is related to how do you do science, because what he mentioned is our established facts. He's measuring the temperature today, but he's backtracking. He can reconstruct the temperature of 100,000 years back. How does he do this? It's a lot of work. I mean, there is no free lunch. It's a lot of work. In fact, if you go to his lab, we are based in a campus in Via Torino. It's the modern facilities. One of the floors of one building is completely dedicated to his lab, because he has clean rooms. They have to do very detailed measurements. This is which otherwise everything is spoiled. You need an international team in order to do this, and you need fundings. So I want to, ask Carlo, what is this? Because Carlo is leading an international team, and everyone, in this big team, everyone needs to know his role, and so ruling this team is not a piece of cake, right? It's a lot.
No, I mean, they are sucking my life, yes. Basically. No, I mean, the group is pretty big. We are part of an international team. That's correct. We do also have a team of the university and of the CNR. Actually, at the campus, we do have the Institute of Polar Sciences, which make a group altogether from CNR and university of about 45 permanent staff. Is almost a department, working on different aspects of our cryosphere and different archives, different way in which we reconstruct the climate. Is pretty complicated, and also managing people coming from different domains with different stories is a challenge. And also when you run international projects like the one we are now, I didn't mention, but I show the 800,000 year record of climate, and well, it was a project that finished about nearly 20 years ago, and now we are seeking for ice as old as 1.5 million years, so nearly double that record, which is per se, of course, doubling the record, but about 1 million years ago, there is a period of time which is called the mid-Pleistocene transition, about which we don't know what happened to our climate system. It changed the frequency and the amplitude. And of course, it was not because of human beings. We had our ancestors were already around. And by the way, there is a paper in Nature of a few months ago that showed that during the mid-Pleistocene transition, our ancestor had a sort of bottleneck in the evolution, and they survived. There was about 1,300 hominin that survived during that period of time. So we are here because of these 1,300 brave hominin that could bring our genome and develop into that. So we don't know exactly what happened in that period of time. So we are very much interested to reconstruct the climate of the past. We are now drilling in Antarctica again. So we are almost 1,837.42 centimeter down. So I count centimeters. Hopefully next year we will touch ground, so reaching the bedrock, and hopefully at 1.5 million years. So we are very much interested to look at this very precise, specific period of time. the mid-Pleistocene transition. I had it online.
You had a question online.
Well.
Oh no, I think they're saying how wonderful.
No, so, okay, no. Grazie, Shaul. Grazie, Shaul. Thanks, Eva, for your comment.
Any questions from the room? Yeah.
Grazie, Carlo, for the very nice presentation, as usual. I have perhaps more technical questions on the scenarios, because especially within, I would say, the modeling, socioeconomic modeling community, now we tend to think that the SSP5, 8.5 scenario is, at least from the socioeconomic narrative, is not something really plausible and likely. So we rule that out as very unlikely because of the socioeconomic drivers that are behind. But if I got your message right, what you were trying to suggest is that maybe the socioeconomic narrative is, let's say, not likely, but there are so many uncertainty and things have been going much faster than we expected that still it could be possible for other reasons other than economic reasons, let's say socioeconomic reasons, because of uncertainty in the climate system.
Yeah, of course.
So is it the case, or is this a scenario that perhaps when we do impact assessment, we should still keep in mind as high-end possibility?
Yeah, I think so. Modeling is very difficult, and one of the things we are also trying to reconstruct the past is that we use the model, the model that will project into the future, and we try to foresee the past. You know, understand me? We test the model on the previous data we have. So if the model works well in the past, we have good chance that it might work into the future, although conditions are changing and forcing is changing. And again, they are models, they are mathematical equation. And one of the colleagues that is doing modeling, he told me, well, models are like sausages. Everybody likes it, but nobody knows what is inside. So that's true from one point of view, you know, because you have to really keep it and tune it them very well, to test, to prove, to test and prove. But we owe a lot to the models, because they help us a lot to understand the processes and to also to make the projection. I think we admit we are not perfect and we don't understand that, and the more we learn, the more we increase the accuracy and the precision of the model, the more we see that well, we might have underestimated something that we were giving for granted in the past. So, well.
Yeah.
Thank you very much for your lecture. Extremely, not all new, but extremely kind of put us on the spot. I noticed that you, so also in the definition, the social economic, social political, social economic model, and also in all your talk, you've not mentioned, and I wonder why that is, the potential role of ecosystems as, I know they play a part in the stability of the climate in the Holocene. So maybe they only play a little bit of a part, but are there models that include potential ecosystem recoveries? I mean, I know this is unlikely, but I wonder if they're part of any of these models also. And so it's not just reducing CO2 emissions by replacing fossil fuels by renewable energy, but also including CO2 capture, recapture into living systems. Is that part of your modeling at all?
Well, again, I'm not a modeler, so I'm a data producer, but yes, I think that there are models that take into account. So yes, the answer is yes, but I'm not an expert in modeling. Yeah.
Thank you so much. Oops, for the lecture. I was like, we've been talking about like the global changes and these perspectives, and obviously, like me as a student of environmental humanities, like I've studied some of these things, but I've been always curious about how we can like connect our personal experience, like living in a certain climate or environment, to this global like processes. For instance, like I was always curious, this spring, like actually 2 or 1 week ago, my parents from Moscow sent me videos of snowing. Like it was really snowy back then. So we have this like instances of change into like the cold times when it's actually supposed to be getting warmer. Like, can we find, like, is it somehow connected to the global warming in that sense, or is it just an instance of like some other things that are impacting that?
Yeah, that's a good question. Well, first of all, again, I told you the first 4 months of this year were very warm in average. But well, if you look at what happened in northern Italy, I mean, I would say it's pretty cold. It's raining still in May, not that warm as it should be, and so we are measuring average temperature. And again, these instabilities create in the northern hemisphere also instability in polar vortex, you know, and these meander which are formed are more and more intense, you know, and they goes down with cold air masses arriving down. So that means that if you go on the north, you have on it is counterbalanced by the warming in the Arctic, for instance. We had people from the institute that just came back from Ny-Ålesund in Svalbard archipelago, 79 degree north, and in March, where it should be minus 15 as average temperature, it was raining at the station. So, you know, and those effects are enhanced by changes in the atmospheric circulation. So it's clear evidence of a general trend. So the fact that it's snowing in May or April in Moscow doesn't surprise me that much.
Thank you for the presentation. I really enjoyed it and I learned a lot. And what do we do with the Anthropocene? I mean, wasn't the Geological Society a couple of months ago telling us that we don't actually have the Anthropocene? What do we, so we poor humanists, what do we do with that? You know, we've been holding on to the Anthropocene for a while, and now we have to let it go. Should we let it go? I mean, is it useful to have it? I mean, there are many problems about it. I know that, I understand that, but you know, it's been sort of also heuristically problematic in many ways, right? So it's served a purpose, or so. Yeah, please tell us what.
I can tell you, I'm not a geologist, but I can tell you a lot about geologists. It took about 140 years to define where the Quaternary period started, you know. They argue for 140 years. What? The zero, you know, which has now been fixed to 1.7 million years ago, something like that. They discuss for more than 140 years. Well, so you think I think we can wait. No, I mean, we can wait to have a definition where the Anthropocene can start, you know. So it's not our fault, but we are living in the Anthropocene.
But what I'm saying is that conceptually, you think, is it something that conceptually we want to hold on to as an umbrella term?
Well, I think it's
apart from, you know, that, you know, can sort of, that does something in, you know, in terms of both the scientific data and also you know, well, does the work of you know, theoretically.
You can call it however you want, but the evidence is clear. I mean, we are overcome the threshold on which the humans are really affecting climate. So we are an active part into the climate system, and that was not the case until 100 years ago. You know?
Yeah.
My question is a little bit related actually to yours about the concept of the Anthropocene. I mean, there's no question that a driver of change is anthropogenic, but when it comes to naming any past era, we don't name it after the comet that hit the planet and potentially created the change, or the names of the volcanoes that erupted and potentially initiated a cascading change. The actual name of the Holocene or other eras have always been more about the after effect, the world that is created, and the overall kind of that once it's kind of transformed, then the Holocene is a period of stability. Holocene, the name to me reflects that for life. And so I'm just curious, related to your question, if we actually conceptualize about the potential of where we're going, if we were to go into another hothouse era, if we aren't able to stop the cascading effects, how would you describe what that world would be like? Like imagining that potentially. Would it be a flooded planet? Would it be, like what would kind of be the qualities that we might actually then name the next era, which we are a catalyst of? But
I think we will leave to social scientists to define the
or the literary, or the poets and artists.
exactly.
What the physical world would be.
Well, imagine living. I'm thinking about 2,300 with 6 meters higher sea level. Well, I think we will have a huge dam in front of Venice. We argue and we thought about how to protect Venice in the 70s, the previous century, and how to protect. Are we building a dam? Are we building a dam like in the River Thames in London, which brings and goes back and forth? But you see, so is a visual impact. So we decided to have everything hidden into under the sea, under the lagoon. But it will arrive a day in which we have to make choices. So we have to think whether we want to save the San Marco Basilica, or we want to save the fish of the lagoon, or the fish, or I don't know how to all the species of the lagoon. We have to make choices, and it will be completely different than it is today. And 200 years is tomorrow from a geological point of view. It's literally tomorrow. And again, we are living from a climatic point of view in what is called an abrupt climate change. So we are definitely in. So we have to take actions. We have to live with no resources and no ice in the mountains, with an increasing sea level. So I took the example of Venice, but imagine what happened in other regions of the world which are already affected by sea level. Imagine the tropical, exactly. Well, we have already the models today. Regional models tell us that there will be a dipole in the temperature in winter and summer. We will have warmer temperature in the southern at this latitude, and the vice versa. We will have colder winter in the colder winter in the northern latitude. So there will be a sort of dipole into the system. I think we have to live with that. We have to try to mitigate, of course, but again, we have to adapt and to suffer.
So I guess part of mine is wondering if we are going to adapt, to start modeling what the world is going to be in this time space, and then how.
We already have an idea. We already have an idea, and the model tells already how it will be from a physical point of view. I mean, in terms of temperature, sea level, from economical point of view, everything is there. But we have to take a decision. We have to take action. It's something that, and we shout with the politics, and with our politician, but it's not always easy. Yeah.
Preaching to the converted.
We already know that 10% of the human population
No, it's all there. We know, and we have the solutions. And we have the solution from a scientific point of view, from a technical point of view. Laws, I mean, if I look at the European laws, I think we are there. From an economic point of view, we are there. Financial is there. Well, politically, we are not there yet. We are not there. We are not able to take decision. And I tell you, can I take a couple of more minutes? I'm part of a pool of scientists, which is called La Scienza al Voto. I hope you can understand what I mean. So we look at the a group of scientists reading what the political parties is doing. We do it in Italy, We did it in for the political election in 2018. So we were screening all the programs, even with the search of the word, looking at the program climate. No one of the program we look at that in 2018 there was a word climate. Well, that was a bit worried. Then we did it in 2022. We gather all the political parties and say, you have to put this because that should be in your agenda. So every party had climate, or at least different. Well, the word was there. Then when you had to go to look at that, okay, so and so, but at least it was there, and some of the parties were pretty good in the way in which they tackled that. So we did it last on May 3rd again for the European election. We gathered all the people. We had it in Palazzo Franchetti with foreign parties, with some of the Italian parties showing their programs. Well, I can tell you, it was really frustrating, listening some of the people that they will be the people that take the decision for us and the policymakers in the future. That was really, really frustrating. I wouldn't put my son and daughter in their hands, but well, some of them will step in. It is really really frustrating to see the poorness and the nothing taken into account properly. I can give you an example if you want when we close the mic off the records.
So thank you very much, Carlo, for this,
It's a pleasure.
Professor Barbante, and see you all soon.